Sorry that it took so long to make this video. Trust me, I'm tired. I'm very tired. Okay, so my name is Bam Bam, as we all know, but that's not my name actually. My name is Victor, but then I'm popularly known as Bam Bam. I think somebody said I should name my tutorial Radio Revolution, but then that's weird. That's really weird. Okay, I must say this is very weird teaching a phone. I don't know. I might be weird. It might sound crazy. But well, we just have to do what we have to do. Yes, 428, that's radioactivity. So we're going to be doing 428, which is radioactivity, right? Now, radioactivity is what is the disintegration of the nucleus of an atom with the emission of radiation and energy. That's basically it. With the emission of radiation and energy. Obviously, if you go to the gym and you want to reduce your size or you want to change your size, what do? You work out, and when you're working out, what are you releasing? You're releasing sweats, you're burning energy. So that's basically it. You can liken it to working out. In case you have a very difficult way of understanding it, just liken it to working out. Alright, thank you very much. So now there's two types of radioactivity. We have two types of radioactivity. We have the nuclear radioactivity. Not nuclear. We have the natural radioactivity and the artificial radioactivity. Yes. So there are two types of radioactivity. We have the artificial and then we have the natural. Now, I'm going to put the table and then we're going to talk about two of them. Natural and artificial. Now, the best way I can explain this to you. Now, for natural. Natural is basically, how do I put it? Something that occurs naturally. It is disintegrating because it's unstable. Are you with me? The nucleus is disintegrating because it is unstable. It wants to become stable. But you see this guy artificial. See all those girls that used to see that they are slim naturally. Sorry, I'm using girls. I'm so sorry, girls. I'm sorry. Okay, don't worry. I'll use boys. I know you guys are offended, so I'll use boys. So you see all those boys that they are lanky, that they don't have anything in their body. You understand what I'm saying now? Exactly. Boys, if you like vest, now you sabi. So yes, you see all those guys, they would take steroids, take things just so they can, go to the gym and then push up, and then next thing they are bloated and then they have muscles. Now if you notice something, when they stop working out, what happens? They become fat. Or the whole muscle become flappy, which is terrible. So yes, that's what happens in natural radioactivity. An atom, an element that is naturally stable will out of nowhere say, no, I want to exhibit disintegration. So because he wants to exhibit disintegration, that is because he wants to perform radioactivity, he wants to become a radioactive element. So what he does is that it will go and bombard itself with a radioactive particle, just so that it can also change. So basically, if you are defining natural radioactivity is the spontaneous. Now why am I saying spontaneous? It is fast. It happens very fast. It is spontaneous disintegration of heavy, unstable nuclide. It is a spontaneous disintegration of heavy, unstable nuclide with the release of radioactive particle and energy. With the release of radioactive particle and energy. I hope you can see this. When you cannot see it, I just said it. I said natural radioactivity is defined as the spontaneous disintegration of heavy, unstable nuclide with the release of radioactive particle and energy. Why artificial? It is the disintegration. Now if you notice, I did not say spontaneous, meaning it's not fast, it's not spontaneous. It is the disintegration of a stable nuclide. Imagine. Why are you changing if you are stable? That's weird. So it's the disintegration of a stable nuclide by bombardment. By bombardment of the nuclide with a radioactive particle to release other particle and energy. Are you with me? Are you there? So it is the disintegration of a stable nuclide by bombardment of the nuclide with a radioactive particle to release other particle and energy. Obviously, if I say disintegration of a stable nuclide, meaning that the stable nuclide is changing from one state to another. So don't come and be asking me what is it changing to, what is it disintegrating to. It's definitely going to disintegrate, meaning it's changing from one nucleus to another. So there's a change there. Now, if you're going to talk about the differences between them, I already made mention of some of them. Now, one of them is that what? This one occurs what? Naturally. Are you there? This one occurs naturally without any human intervention. Why this one? What happens to this one? This is a kind of radioactivity that is induced. It is induced in a non-radioactive substance, as you can see. The substance is not radioactive. Now, how do you know a radioactive substance? Sorry, I'm too fast. I'm sorry. Let me take it slow. How do you know a radioactive substance? A radioactive substance are heavy, unstable nuclides. Are you with me? They are heavy and they are unstable. That's how you know that this is radioactive. So when it's stable like that, it's a non-radioactive substance. So this artificial radioactivity, what happens? They are basically it's a radioactivity that is induced in a non-radioactive substance by particle bombardment. So this one is a naturally occurring radioactivity, meaning nobody is touching it. Now another thing, this one is spontaneous. This one is not spontaneous. Now this one cannot be controlled. Why this one can be controlled by controlling the speed of the bombarding particle. You cannot control this one, cannot control natural radioactivity, but you can control the artificial radioactivity because you are the one that is bombarding it, you are the one that is adding, so you can control that. So that's that. So that is basically all for the differences between them. If you want more information, buy the past question. Thank you very much. Now moving on. Now that we've spoken about radioactivity. We've spoken about radioactivity, yes, we've not even given any equation. So let's give an equation for natural radioactivity. Let's show an expression for natural radioactivity, and then we'll show for artificial radioactivity. So our example is thorium 23290 to give us let's see, what would it possibly give us? Let's say it gives us radium 22888, thereby releasing helium particle. Now, if you look at this very well, thorium is disintegrating. This is a very fast process. Thorium is disintegrating. That is, it is changing from thorium to radium. And how is it doing that? By emitting alpha particle. Now, if you want to know if this equation is balanced, all you have to do is 228 plus 4, because alpha particle is 4. 228 plus 4 will give us what? 232. And then 88 plus 2 will give us 90. So the equation is balanced. So what happened here is that thorium emitted helium, that is, emitted an alpha particle, thereby forming a new nucleus, which is the radium. Now, but in artificial radioactivity, you have aluminium, which is a stable nucleus being bombarded with a neutron to give us sodium and helium. So we have aluminium, which is a stable nucleus being bombarded with a neutron to give us sodium and helium. That's an isotope of sodium. Sodium is naturally 2311 Na. Sodium is naturally 2311, but that's an isotope of sodium. So this is artificial and then this is natural. Now I think I've spoken about particles. So let's dive into particles the more. Now when you talk about particles, you're basically talking about radioactive particles. And then I know from secondary school knowledge, you have 3 main radioactive particles. True or false? True. The one that they told us about is alpha, beta, and gamma. So we're going to talk about those 3 because those 3 are the most important ones as well. Nothing changed. It's still secondary school knowledge. Nothing has changed. Nothing at all has changed. So let's talk about it. Let's talk about them then. So let's go first with the alpha particle. Alpha particle is also likened to helium. Alpha particle is the same as helium. It has a mass of what? Of 4.002603 atomic mass units. It is heavy. See that? 4.002603 atomic mass units, which makes it heavy. And because of that, it has a very low penetrating power. it has a very low penetrating power. Are we there? It has a low penetrating power. Now, ordinary paper can shield you from the radiation of an alpha particle. That's something about alpha. Alpha is not that harmful. Now let's go to the next one. Next one we have is what is beta, which we usually represent in this B. This B that has long legs. Yes, beta. Beta 0, -1. Beta does not have a mass. It does have a mass, but we usually say that it does not have a mass. It has a mass of, sorry about that. Beta has a mass of 0.0005885 AMU. Yes, that's a mass of 0.0005885 AMU. And that's beta. Beta is also electron. You can also say, either you say it's beta or you call it electron. But this is the negative beta particle. We have two beta particles. We have the negative beta particle and we have the positive beta particle. As you can see, the negative beta particle is the same thing as electron, which is a negatron. While the positive beta particle is called a positron. Are we there? It's called a positron. So what happens with beta particle? They have a moderately, they have a charge of -1, as you can see. Their proton number is -1. You know now, the number that is here, their proton number is it's -1. So they have a moderate. It's not too high, it's not too low. They have moderate penetrating power. They have moderate what? Penetrating power, meaning they can penetrate buttons. You understand? It's moderate. It's a moderate penetrating power. Yeah, we are thinking nonsense. Don't think nonsense. It has a moderate penetrating power. So that's basically it. That's it for beta particle. You need a lead apron or lead sheet to shield you from the radiation of a beta particle. That's something about beta. You need a lead apron or lead sheet to shield you from the radiation of a beta particle. Now let's go to gamma. Gamma. They usually tell us that gamma ray has no mass and no. Let's talk about gamma. Yes, gamma ray. As you can see, I call it gamma ray and not gamma particle. Gamma is not really a particle. It's a plain, pure energy. Photon energy to be precise. It moves in waves. It's a plain, pure energy. Photon energy. And it has a very high penetrating power. Let me tell you why it has a high penetrating power. It does not have a charge or a mass. So it has a very high penetrating power. Are we there? It has a very, very high penetrating power. You need a lead wall or concrete to be able to shield yourself from the radiation of a gamma particle. And now when you come in contact with gamma ray, it can cause your skin to burn. It can cause your DNA to be reconstructed. It can damage your genes. Are we there? It can, what again? It can cause your organs to begin to fail. So that's basically all for gamma ray. That's all for gamma ray. Now we have one more. And I'm sure you have seen that one. The one we call neutron. It's also a particle with a mass of 1.008665 AMU. So that's neutron. That's a mass of 1.008665 AMU. Yes, just take that down. Just note that down. Make sure you note that down. So now let's go to something called. Let's go to what we know as. Let's go to radioactive series. Now I'm going to ask a question. Is that called radioactive series or you call it decay series? Radioactive series or decay series. Now question. What is radioactive series? Now I've told you what radioactivity is. Now I'm asking you series. Now link it together. I said radioactivity is what? It's in disintegration of what? Of a radioactive of a nucleus of an atom. Abi? Radioactivity is what? It's the disintegration of a nucleus of an atom with the release of what? With the release of radiation and energy. So they are releasing radioactive particle and energy. Now let's talk about series. Now, continuous. Are you saying that? A sequence. Meaning maybe you disintegrate a nucleus once and then the thing is not it's not stable. What will happen? You disintegrate it again. Maybe it's not stable again, you disintegrate it again. It will continually emit particles in the process of disintegration until it forms a stable product. So that's what happens here. So you might be asked in the exam, they will ask you, what do you understand by radioactive series? What do you understand by radioactive series? So let me explain that to you. Now, when an unstable nucleus disintegrates, it forms a product. To form a product, the product formed might not be unstable. If you are writing, the product formed might not be unstable. So what happens? It will further disintegrate. Are you with me? It will further disintegrate until a stable product is formed. In the process, you will be releasing, obviously when you are disintegrating, you release particles and energy. So that's basically it. So when an unstable nucleus disintegrates, the product formed might not be unstable. So it will undergo further disintegration until the stable product is formed. So that's what happens in radioactive series. Now we have examples of radioactive series. We have the thorium series, we have the uranium series, we have thorium series, we have uranium series, we have what's the other one again? Actinium series. Yes, we have thorium series, we have uranium series, and we have actinium series. I don't know if I'm going to, should I give you that? That will take my time writing it out. But let's try, let's do it. But I'm going to give you for thorium series first. Let's give you for thorium series. I'm giving you for thorium series because they only ask you for one in the exam. So you only need to know one. Exactly. So let's deal with thorium series. So thorium 23290 will undergo 12 disintegration steps to give us 20882 lead. So that's the stable product. Thorium will undergo 12 disintegration steps until 20882 lead is formed. Now let's look at how we can do that. Now, in the process of disintegration, don't forget, particles will be emitted. Now let me write out the cheat code of how you can, because it's not like maybe I'm the one that decided how I can disintegrate thorium. It's not me. Somebody that carried out this experiment already. So I'm just going to show you an easy way to cram it, because obviously you're cramming it. So first thing that is emitted is alpha, then emitted is beta, then alpha again, then alpha, then beta. Then here you have alpha, beta, and then you have beta, alpha. Let's count. Sorry about that. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 steps. So the first thing you're emitting is alpha, then beta, then alpha, then alpha, then beta, then alpha, beta, alpha. So let's go. Don't forget, emission means subtract. If I say you are emitting something, it means you are subtracting that thing from what was initially there to give the product. So let's do this together. Don't forget that helium is the same thing as alpha. So alpha has 4 up, 2 down, while beta has 0 up, -1 down. Do not forget that. Let's go together. Let's go. So first step, 232 thorium. 232 thorium. So thorium will emit alpha particle. Now by emitting alpha particle, permit me to do this. Thorium will emit alpha particle. Thorium will emit alpha particle. By emitting alpha particle, I mean, it's 23290. Alpha is 4 and 2. So let's subtract minus. So you subtract 232 minus 4, which will be what? 228. And then 90 minus 2, which is what? 88. So it means that the up here we have 228, while the down we have 88. And the element with this atomic number is what? Is radium. So you need to know the elements with each atomic number. So that's radium being formed. And now this happens for 1.39 times 10 raised to the power 10 years. Now you might be wondering, how do you want to cram these years? I don't know. I really don't know. I don't know the easiest way to cram the years, but that's just basically it. Now the next thing that will be happening here is what? Is beta emission. Beta. Now, come back here again. Beta is what? Is 0 up, is minus 1 down. But don't forget that we are subtracting from here. So basically 228 minus 0 is also 228. But 2288 minus 1. Because it's minus, it will turn to what? It will turn to plus. So it becomes 89. So here you have 228, 89 actinium. Yes, that's what you have. 228, 89 actinium. So let's keep going. I said the next thing that will happen again is what? Is beta. Beta emission. So beta again, 228, 89. Subtract 0, subtract minus 1. Becomes what? 228, 90. So we're back to 228, 90. Thorium. So we're back to thorium again. Now, sorry I forgot to make mention. This one occurs for 6.7 years, while this one occurs for 6.13 hours. Forgot to put that. So please, I'm very sorry. Please make sure you rectify that for me. Now, moving on. I'm continuing from that place, but okay, I think I should put it down here. Is this better? Or should I start again from the beginning? I think I should start again from the beginning. So from there, we will have another alpha emission, that is from 22890 thorium. Yes, from 22890 thorium, that 22890 thorium, we have an alpha emission. Alpha means what? We are subtracting 4 from up, 2 from down. So 228 minus 4 is 224. 90 minus 2 is 88, which is what? Radium. As you can see, we're back to here, 88 radium. And this happens for about 1.9 years. Happens for 1.9 years. Yes, that happens for 1.9 years. Let me hold my book so that I don't make any mistakes. I'm forming scholar for you guys. No guys, so yes, moving on, we have another alpha emission. This happens, this is 224 minus 4, which is 220. 88 minus 2, 86. This is radon. This happens for about 3.64 days. Am I correct? Yes, I'm correct. 3.64 days, yes. So the next thing there is alpha again. I told you 4 alpha after the beta, so alpha again. That will be 21684. This is polonium, and this happens for about 54.5 seconds. Is it 54 or 58? 54.5 seconds, I'm correct. Yes, 54.5 seconds. Now, this polonium guy, let me start from here again. Polonium 21684, yes, will undergo alpha again, which will now give us 21282 lead. This happens for about 0.158 seconds. Now, why is it giving us lead? Don't forget, 216 minus 4, 212. 84 minus 2, 82. It's looking like this is our final product, right? But that's not our final product. We're going to 20882 lead. Don't forget. So now, from here, it will emit beta particle. Beta means what? Subtract 0 from up, subtract minus 1 from down. If you are subtracting minus 1 from down, it means you are adding 1 to the down. So that will be 21283 bismuth. This happened for about 10.6 hours. So from here now, this is where the magic happens. From here, you have one going up and you have one coming down. This undergo alpha, this one undergoes beta. This happens for 60.5 minutes, and this one happens for 60.3 minutes. Are we there? 60.5 minutes, 60.3 minutes. Are you getting it? I hope you are getting it. Now, let's see how alpha is being emitted here. Alpha means subtract 4 from up, 2 from down. So 212 minus 4, that should be 208. 83 minus 2, that's 81. This should give us thallium. Are you seeing it? TL, thallium. Let's talk about beta. Now this is 212, this is 83. Beta means 0 up, minus 1 down. So 212 minus 0 is still 212. But 83 minus 1 becomes 84, which is polonium. And then for the final product, this has already undergone alpha, so to undergo beta. This has already undergone beta, so to undergo alpha. This happens for 3.0 times 10 to the power minus 7 seconds. Why this happens for 3.1 minutes. And then the final product. I said this one happens for 3.1 minutes, this one happens for 3.0 times 10 to the power minus 7. And the final product is 20882 lead. 20882 lead. So that's all you need to know about radioactive series. So this is an example of, let's move on. Half-life. I'm sure you've heard of half-life, because obviously there's no radioactivity without half-life. What do you think? There's no way a radioactive particle will decay without us taking note of the what of the half-life. So what is half-life? Think about it. I know you know. Oh yeah, just tell us. Talk the nonsense that's in your mind. Okay, well, let me let you know. Half-life is the length of time it takes for half of an unstable nuclide to become stable. What did I say? The length of time it takes for half of an unstable nuclide to become stable. So basically I'm saying if the unstable nuclide was initially 10, after one half-life period it should become what? 5. If it was initially 2, after one half-life period it should become 1. So half-life is the length of time it takes for half of an unstable nuclide to become stable. Now let's show a relationship between half-life and decay constant. I hope you know what decay constant is. Now you know that formula that you used to write as T half equals to 0.693 over lambda. Yes, that formula. Ola, you know what I'm saying. T half, Abi. Yeah, and T half is the column. So yes, half-life is the length of time it takes for half of an unstable nuclide to become stable. But then this is the formula for half-life that we all know, right? Now let's figure out how this formula was derived. Who will work with me? Let's go together. Let's figure out how that formula was derived, because in your exam they're going to ask you. Let me see the question. They're going to be asked, from the radioactive decay equation, derive an expression to show relationship between decay constant and half-life. This is decay constant. Lambda is decay constant. And then this is half-life. So let's show the relationship between them. Let's show how the relationship existed between them. So let's go. Let's go together. Permit me to divide the body into 2. So first of all, a radioactive reaction. A typical radioactive reaction is A will give us B plus X plus delta E, where A is parent nuclide and B is daughter nuclide, and X radioactive particle. While delta E is obviously what? Energy. Yes, so that is a typical radioactive reaction. Are we there? A typical radioactive reaction. Now, you know, back then when we were doing chemical reactions, we were dealing with chemical reactions, we always said that the rate of a chemical reaction is directly proportional to the what? To the concentration of the reacting particle, isn't it? Yes, but unfortunately this is not chemical reaction, this is a nuclear reaction. There's no concentration here. So basically, the rate of a chemical reaction is dependent on the amount, are you there? On the amount of the reacting particle, the amount of substance of the reacting particle, the amount of this substance, the reacting substance, the amount of it, which is represented as N. So you have rates to be directly proportional to N, where N is what? Amount of substance. N is amount of substance. Are we there? N is the amount of substance. So if rate is directly proportional to N, in order to you know what rate is now? Rate is minus the N over dt equals to directly proportional to N. This is supposed to be your equation 1, but just chill. You get there. Now, in order to eliminate the proportionality sign, what do? We bring in a constant. That constant is what we know as the decay constant. So you have minus the N over dt equals to lambda N. Where lambda is what? Decay constant. Where lambda is equals to decay constant. Are we there? Lambda is the decay constant. Now, I remember telling you in chemical reactions that's in 413 that whenever you are met with a situation like this, you're trying to make N squared the formula. So let's make N here subject of formula. In order to do this, you with me? In order to do this, first thing you do is you cross multiply. So cross multiply. When you cross multiply, you have what? You have minus the N equals to lambda N dt. Then the next thing you do is what? You divide both sides by n. So divide here by n and divide here by n. N will cancel n. You are left with the n over n. You know this one cannot cancel. This one is change in the amount of substance. That is change in that radioactive substance. Why this one is what? The amount of substance itself. So you cannot what? You cannot cancel each other. So what you do here is what? You minus the n over n equals to lambda dt. So here you are integrating. Then integrating with respect to two things. The first one is what? To t equals to t. The second one is t equals to 0. You are integrating with respect to t equals to t and t equals to 0. Are you with me? You are integrating with respect to t equals to t and t equals to 0. Please stay with me. Stay with me. Thank you very much. Now when you integrate if you integrate the n over n naturally, you will get ln n. If you integrate the n over n naturally, you're supposed to get ln n. But now you are integrating with respect to t equals to t and when t is equals to 0. So you have two values, and that values will be minus because of this minus that is here, just like the minus is outside. Are you with me? Because of that minus. So minus ln nt minus ln n naught. So the first one is for what? T equals to t. The second one is for what? T equals to 0. Which will now be equal to, here too we have the same thing. We have lambda t because there's dt here. When you integrate dt, you get t. So lambda t minus lambda 0. So this is what you now get. Are you with me? This is what you now get. So coming back here. Now I don't need to be writing two lanes here, it's unnecessary. You can just use one. So by doing that, you say minus lane what? N over n naught. You can choose to put the nt, you can choose to remove it. So I'm removing it for now. So minus lane n over n naught, which is now equals to lambda t. The next thing I advise you to do is to eliminate the minus sign, please. Just eliminate the minus sign. Eliminating minus sign will become multiplying both sides by minus. So multiply by minus 1. When you multiply both sides by minus 1, you have ln n over n naught to be equals to minus lambda t. Are we together? Where n is amount of substance at t equals to t, that is at any point in time. That's the amount of substance at t equals to t. And n naught is the initial amount of substance. N naught is the initial amount of substance. N naught is the initial amount of substance. Are we there? So yes, let's go. I forgot to make mention. The previous equation is your equation 1. There's the equation down there is equation 1. I'm sorry I didn't make mention of that. I will show you. This is your equation 2, and then this is your equation 3. Sorry, this is your equation 3. Yeah, that's your equation 3. Please, I will show you what your equation 1 is, but this is your equation 3. This is your equation 3. So moving on. Let's move on. Now, if you take exponential, taking exponential of both sides will give you exponential ln n over n naught equals to exponential minus lambda t. Exponential cancels exponential, you have n over n naught to be equals to exponential minus lambda t. At this point, you cannot make n set the formula, right? So n is now equals to n naught exponential minus lambda t. Abi? But if you notice, we have still not shown the relationship between decay constant and half-life, right? So let's do that. Let's show the relationship between decay constant and half-life. Now, from equation 3, we're going to go back to equation 3. I'm sorry, people of God. This is your equation 4. We're going to go back to equation 3, which is ln n over n naught equals to minus lambda t. Now, ln is equivalent to 2.303 log. If you don't know this, you now know it. Ln is the same thing as 2.303 log. So with that being said, I can replace this with 2.303 log n over n naught equals to minus lambda t. Abi? I'm sure of that, right? Yeah, so let's go. Now with this being said, this is your equation 5. That's your equation 5. With this being said, remember I said half-life is the length of time it takes for half of an unstable nuclide to become stable. Now we know that n naught is the initial amount of the unstable nuclide, right? So after a given period of time, n will now be the current amount of the unstable nuclide. So now I'm asking, after one half-life period, if n was 2, what will n, sorry, if n naught was 2, what will n become? N will become 1. If n naught was 2 initially, after half-life period, n will become 1. So definitely this one becomes half of whatever this one is. With that, I can say that after one half-life period, the length of time, after one half-life period, the fraction of n over n naught becomes 1 over 2. The fraction of n over n naught becomes 1 over 2. And if that is so, we have 2.303 log 1 over 2 equals to minus lambda t. True or false? True. Now, 2.303 log 1 over 2. If you punch your calculator, people of God, you should be getting minus 0.693, which will give us minus lambda t. Minus will cancel minus. This is where you have, half-life. I forgot to make mention. Don't forget to put your half-life. Because the moment is after one half-life period, the t is no longer t, but now t half. It's not half-life. So, at this point, lambda is equals to 0.693 over half-life, or half-life is equals to 0.693 over lambda. So this is how the relationship came about. This is how they got this formula. I hope it's clear. This is how they got this formula. Now don't forget all these equations that I've gotten, this equation 3, equation 4, and equation 5. Please, we're going to use them to solve questions. So get your mind ready. Just get your mind ready. Okay, are we together? Now, for the sake of graph, because you might be asked to solve graphical questions. So now, for the sake of graph, there is a derivation I'm going to give you. You don't need derivation. You don't need to know it. You don't need to know the derivation. You just need to know the end product of the derivation. Are we there? So for the sake of graph, let me show you something. From equation 3, from equation 5. From equation 5, that is the 2.303 log n over n naught equals to minus lambda t. Yeah, that one. This particular one. This equation 5. Yes, this particular one. Now, if you look closely, as you can see on the board right now, you look closely, if I divide both sides by 2.303 divided by 2.303, I would have log n over n naught equals to minus lambda 2.303 t, right? Now I can write this log n over n naught as log n minus log n naught, which will be equals to minus lambda over 2.303 t. Are we there? Now, with that being said, I want to make log n set of formula. If I do that, I'll say log n is equal to what? Minus lambda over 2.303 t plus log n naught. That is, this guy came over here. With this, you can see that this will be your y-axis, this will be your slope, this will be your x-axis, and this will be your intercept. Are we there? So I can now say that a radioactive graph, please take note, a radioactive graph is always a graph of log n against a graph of log n against time t with a slope of minus lambda over 2.303. So it's always a negative graph. Are we there? It's a negative graph. It's a negative graph, abi? With an intercept of what? With an intercept of log n naught. With an intercept of log n naught. Please do not forget that. So you need this graph. You need it. You need all of this information to solve graph questions. I don't know if we'll be able to touch graph questions on the board because it seems really well, but I'll try and solve one for us. I'll be there. I'll try and solve one. But let's take questions. Let's take questions. Okay, quick question. Quick question. Let's solve this one. The question goes like this. Charcoal sample. I hope you're writing this down. Charcoal sample. I cannot start writing question on the board. I'm sorry, I cannot. So please take down the question. Charcoal sample from Enugu. Charcoal sample from Enugu in Nigeria emits, underline the word emits 62.3% of the disintegration per gram. Let me come again. Charcoal sample from Enugu in Nigeria emits 62.3% of the disintegration per gram of carbon per minute expected of living tissue. Full stop. You can use this question, please. Expected of living tissue. Full stop. The question says, what is the age of this charcoal? I hope you wrote down your own question. Don't worry, I'm going to put the question down there for you to see. So, charcoal sample from Enugu in Nigeria emits 62.3% of the disintegration per gram of carbon per minute expected of living tissue. What is the age of this charcoal? They gave us the half-life. They said that the half-life of carbon is 5,730 years. Please take note of that, don't forget. That's the half-life of carbon. So the question says, charcoal sample from Enugu in Nigeria emits. It says it emits what? 62.3%. They did not tell us the initial amount, did they? No. But they said that the charcoal sample emits 62.3%. If the charcoal sample emits 62.3%, what was the initial amount of that sample? 100, right? Obviously, it has to be 100% before you can emit something. So our N naught will be equals to 100%. What will our N now be? I know you are thinking our N is going to be 62.3%, but no. The question says the charcoal sample of 100% emitted 62.3%. So what will be remaining should be 100 minus 62.3%, which is what? 37.7%. So let me come again. It says charcoal sample from Enugu emits 62.3%. They are already telling us what it emitted. They did not tell us the percentage at which it was before it was emitting something. Neither did they tell us what it is now. They only tell us that it emitted something. So obviously, being the fact that they're dealing with percentage, we know that N naught should be 100, and then N will be 100 minus whatever it had emitted, which is what? 37.7. So you can use the formula 2.303 log N over N naught equals to minus lambda T, or you can use the other formula of ln N over N naught equals to minus lambda T. Any one of them that you choose to use is fine. You can choose to use any one of the formulas there. The choice is yours. The choice is basically yours. Alright, so moving on. Let's quickly calculate it. Let's solve it together. So how to use the 2.303 log N over N naught equals to minus lambda T. But the problem is that we don't have lambda, do we? No, so we have to find lambda first. So lambda is equals to 0.693 over half-life. They gave us half-life, right? 5,730 years, which is 0.693 over 5,730 years. This should give us 1.209 times 10 raised to the power minus 4. Calculate it in your own way. 1.209 times 10 raised to the power minus 4. That's what it should give us. Please make sure you are using your own calculator. Don't depend on my calculator. I can be wrong. I'm not Jesus Christ. I can be wrong. People of God, I can actually be wrong. I'm coming. I do not have my calculator with me, but okay, yes, moving on. 0. Yes, that's what you get. So moving on, you now have to please punch calculator for me. 2.303 2.303 log n over n naught equals to minus lambda t. Abi, please, I'm going to clean the board. So 2.303 log n over n naught equals to minus lambda t. So that's 2.303 log 37.7 over 100 equals to minus 1.209 times 10 to the power minus 4 t. Right? I hope you are seeing board. I don't know, my marker is malfunctioning. I'm very sorry about that. So 2.303 log 0.377 equals to minus 1.209 times 10 to the power minus 4 t. Yes. So when you punch this in calculator, you get minus 0.975, which will be equals to minus 1.209 times 10 to the power minus 4 t. Divide both sides by 1.209 times 10 to the power minus 4. That's minus. Divide both sides by minus 1.209 times 10 to the power minus 4. This will cancel this. If you punch this one in calculator, don't forget minus will cancel minus. Punch it in calculator, t will be giving you 80.19. Yes. You can give it within that range. I don't know, my calculator is not punching well. So it should give you something like this. 80,070.19 years. If you get that, clap for yourself. For now, I don't know. I think this is where we should end the class. I would plead with you to please subscribe. I'm going to solve the graph question maybe next time, but for now, let's end the class here. Please make sure you take more questions and solve. It's still the same method. Take any question that looks like this and solve. As time goes by, we'll talk more about other things. Please read your book. Please hit the follow button. Sorry, I mean the subscribe. Subscribe, please. Thank you. Subscribe and like. Thank you.